Okay, let me tell you about the next one.
Get a photo.
Yeah, I should take a photo. Okay, next month, we're going to have Zach Tillman here.
Cool.
For those of you who don't know, he's like a superstar in the Clojure community, and he's written things called like Aleph and Lamina and stuff like that. And
Gloss.
And what? And oh, he did he?
Gloss.
And Gloss. And the amazing thing is that he's a factual employee now.
Ooh.
So that's way cool. And the next month after that, we're having Tom White. The Tom White who used to work for Oblong.
And he's awesome.
And he's awesome. There we go. Thank you.
Yeah, but is it the cloud era Tom White?
Is that the Tom White we're talking about? No, different Tom White.
But he's awesome.
He's still awesome. Yeah. So I just want to ask one question. How many people are here because of Rob's cross-post over to machine learning? Oh, 1, 2, 3, 4, 5, 6, 7, 8, 14.
It posted on two meters actually.
Really? What was the other one?
Well, the clouds and the machine learning, right?
Well, yeah. Well, we posted it, and then Rob cross-posted it.
Yeah.
So the union of those two sets of RSVPs came out to 52 people, which is like enormous.
Thanks, machine learning people.
Yep.
You're welcome.
And you guys are welcome to come even when it's not machine learning, because its Clojure is really cool. So I'm going to turn it over to Anshul. What?
You should take a picture of it.
Yeah.
Here, let's go over your screen.
You counted
Let's
one.
just do it.
52 people, yeah, right.
Because this is like historic. This is
Story. Fish story.
this is just way cool. All right, ready? Say cheese. Awesome.
Hey everyone, for people who don't know me, my name is Anshul, and I actually am going to talk to you a little bit about some practical machine learning problems. I'm not like a machine learning expert in any way. I've never studied it in school or anything like that. I've worked at 3 different startups for most of my technical career, and each one in some way involved some actually fairly significant machine learning that became a significant part of what that company did. So I thought I would just step through one. I kept it really high level, just share generally qualitatively what my experience was, and I hope you all have lots of questions about, how did we do this, or why did we do this, and what are other things we considered.
Lex,
Which one?
just try them until it works.
Okay, so currently I'm a co-founder of a company called Unfold. It's a fairly young, little over a year-old startup. It's based here in LA, and we were 2 people, just me and my co-founder, until a few months ago. Now we're 5 full-time people. We'll be 6 soon, so we're growing. Things are going well. There's always a lot to do and a lot to learn. I'll say why we use Clojure as our primary technology language. A lot of that has to do with me trying to solve similar problems at previous companies where we didn't use Clojure. So in some ways, in order to explain the problems I'm going to focus on not using Clojure, and then maybe finish up with a little bit of why Clojure kind of helped. Okay, so just as a little bit of a preview, I'm going to start with, I started out doing web applications, which are, I'm going to use the word CRUD, and I'm going to talk a little bit about that. I'm going to talk about how that kind of eventually transitioned me into doing a bunch of machine learning problems. I'm going to talk about one particular example. It's actually a fairly typical machine learning problem, document classification. But I wanted to go into a little bit of the practical problems with it. I found generally that it seems like some really cool, simple math. You run it and it does things. And it does work. There's some very powerful techniques. But the reality is messy in a way that I was unprepared for. And I thought I'd share some of that learning with you. And then I talk about why Clojure actually solves a lot of those problems. So first, CRUD. So a lot of you, I think, probably have heard this acronym. The kind of basic actions that any web application take, or a lot of different kinds of software products, just, you create some data, other people might read it, or you might read it later, you might update it, and then you might delete it. And it's really just like 4 kind of basic things. You dress it up, make it pretty, you kind of sequence it in a smart way, but you know, it's some straightforward, simple actions. And I think this acronym kind of is used because it's a little bit derogatory. It's like this basic idea, like, oh, anyone can implement a basic CRUD app, you know, anyone could do that. And, you know, I do think that, you know, given Ruby on Rails or, you know, a lot of frameworks, it's true that it's not that hard to build a very basic CRUD app. And, you know, I started out at a company called Athena Health. I was an employee. And it was basically like, well, we'll make a bunch of forms for people to put in. In this case, it was doctors' offices, and they did scheduling, and they did, you know, a few other billing, things like that. But basically, they input some form, we would move some data from here to there, and then we would print it out in another place. And it's just like basic CRUD stuff. But the question was, how can we do more? Like, how can we reduce the amount of human effort involved to produce the same results? And for the particular problems we had at Athena Health, we would find that we had massive amounts of administrative, you know, kind of crap that needs to be done all the time. For every given patient that walks through the door, there would be, you know, hundreds and hundreds of data elements that are created by perhaps 4 or 5 different people, from the patient themselves to a receptionist to the doctor to the nurse to a biller. Like, all these people are touching data. And it just kind of goes on and on. Actually, the whole cycle goes on and on for months after the patient has been seen. And there's just a lot to do. And a lot of that data is not input correctly, and there's all kinds of, there's just a lot of volume of work. So you know, one of the main things that we were always concerned about is, well, how can we do more with less? And, you know, these are the kinds of things that we looked at. So or when you create or update something, well, maybe we can default some of that information, right? And I think, you know, all web forms people start thinking about, like, well, how do you default some information intelligently? But actually, you can get quite sophisticated about what you default based on what time of day it is, who's come in the door, what that patient has done when they've come before, maybe even demographic database of that patient. You can actually do intelligent things to default that data. Validation. So, I mean, obviously we have tons of validation where you'd have a hard and fast rule that such and such could not happen. You cannot enter data if it has the following fields missing or the following fields in the wrong format. But beyond that, there was probabilistic validation. Well, this could work, but, you know, it shouldn't happen often, and it shouldn't happen probably in conjunction with these other characteristics. Similarly, with deleting, now, you know, you can kind of have hard and fast rules, like this kind of data automatically gets deleted all the time, but then you have all kinds of things that are, again, kind of probabilistic. You have to kind of classify things like, well, you know, based on a whole variety of factors, where it came from, who entered it, how many times did you see this exact data element come in that day. You might say, well, maybe that's spam, or maybe by gaming, I mean, in certain kind of social like applications or social settings, you might have someone who's kind of gaming the system. Also with reading data, where you know, we started out, you have like this complicated search interface, you can find the exact record that you want, but if we can be smart about what to put into that query or how to shape that query, we can actually maybe suggest that this is the next thing you want to see without you searching, or if you're going to search, we can actually filter that search list or order it in a particular way that takes into account a whole bunch of classifying, a whole bunch of categories that we've assigned to that data ahead of time. So I wanted to, as I mentioned, go into an example of document classification. So here's the specifics of this one. So one of the activities at the same doctor's office, company that we had a whole bunch of images would come in, just random paper. You know, you try to get as much electronic as possible, but there would be typically 100 to 200 pieces of paper that were generated per day per doctor, mostly in the form of faxes, actually. Like a fax would come in from a pharmacy, from another doctor that says, hey, I need some data from you, or here's that medical record that you requested. It could be someone else who's like kind of asking permission from the doctor to do something. Hey, we're about to administer this medicine to someone. Here's a fax. You remember this person? Is it okay if we just stick them? So like there's all kinds of different forms. They have different urgencies. They need to be routed to a different person, maybe a doctor, maybe some of them can be handled by a nurse or even a receptionist. But they need to be kind of like filed into the right place, and they need to kind of have the right priority assigned so they get to the right person and they can be processed. And this is a huge, huge part of the day for certain people at a doctor's office. Typically, it's getting a little better. This, when we first started attacking this, it was about 2006 or so hasn't been that long. And it's for most doctors' offices, it's still roughly this bad. So the goal was, okay, so what we would currently have is the receptionist at the practice would take a whole bunch of pieces of paper, you'd upload it one by one, you'd sit there and you'd assign a whole bunch of fields to it, right? You'd say, okay, it's this patient, this is, the category it should have, this is what we do with it. And then, the system would take care of, okay, put it in this person's inbox and so on. But just that cost was a huge burden for the practice, and it kind of got in the way of actually practicing medicine in a lot of ways. So this is what we thought about. Okay, how can we get the software to do a lot of this or as much of this as possible? So we have the user dump it all onto a fax machine. All of the things that would come in, they would kind of go through their mail, and they would fax it directly to us. Or if it was, something that they were receiving via fax, we would have their number routed directly to us. So then we would have our kind of automated system, supplemented by a team of humans, actually, classify as much of those documents as possible. And then we would understand that some of them were kind of complex or one-offs that we couldn't do without someone who had a very sophisticated understanding of the domain. So we would route those to a human after the fact. But we wanted to classify everything we could that had a met a certain threshold of confidence. I'll mention, this was a startup. We were probably, about 200 people at that time. This was not something that we were doing a lot of in the company. So it kind of was something we talk about, like, well, what if we could automate this? And then finally, it resulted in a side project. We were like, okay, just take a few hours a week, kind of push this forward. We got enough of something that kind of worked that we kind of got a team behind it. By the team, I mean it was really just me and a product manager and like a junior developer. So, but we got my time, I guess, carved out to work on this. And so it required a fair amount of kind of conversation, like, hey, and it required the company to kind of believe, hey, if this works, this could affect our bottom line in a big way. And I think those three things were really critical for it to even be funded. So here's how we started it. So we were kind of Perl shop. We coded it in, so like side project, I was like, well, okay, I understand a naive Bayesian classifier. It's like a very, now considered a standard or classic technique to classify documents, related to many of the early spam filters and still a part of like kind of common spam filters and webmail, things like that. So we started with some Perl libraries. There were a couple of things on CPAN that we tried, and we kind of, they kind of worked. They kind of did the job, but they would work if you were doing hundreds of documents or maybe a few thousand. But they were clunky, and they didn't necessarily have all of the features that we wanted. They didn't have all of the power that we wanted. They certainly were very, very slow, and the language itself was not extremely well suited to machine learning.
I would stop you right there. Perl is still one of the fastest language after C and C++. So definitely you were doing something wrong.
Yeah,
so
that may be.
Maybe you create object all the time, and instead of you should create object and then just clear them up. But I will
absolutely.
just.
Actually, no, I think that's a very good comment. What I realized later was that a lot of it was the way that we were using Perl. We were using a very object-oriented version of Perl. That was adding a lot of overhead.
When I was working in MySpace, I was doing 270 million search documents in MySpace 2007 with Perl. No other language could do that. We try everything.
Uh-huh.
So Perl doesn't disappear just because it's very fast.
Well,
Did you read it?
well, I appreciate this comment, and I'll say, I'll actually, I have some caveats later, but I'll mention them now. But I will say that this was my personal experience, and I know that there was a lot of different ways of handling these things. And I'll certainly say that when I get into a little bit later, I'll explain why we were doing things the way we were, which was not optimal. But and I think that your mileage may vary, is I guess standard thing. Here's what happened with us. We weren't ourselves able to make Perl, at least the way we implemented it, scale up effectively. What we did do is feed it into a highly optimized C library called Rainbow, and then also a library called Mallet. They're both by Andrew McCallum, which were, again, a highly optimized Java-based program. And so we would have the Perl layer kind of extract a whole bunch of data. It would do a bunch of manipulation on that data. It would kind of output it to the file system. And then we would feed it into these other programs. They would run perfectly fast enough. They would implement the algorithms. And then we would have Perl kind of pick up all that data, do a few more kind of manipulations on the basis of it, and then feed it back into the database. So that worked, actually. That was fine. But then we actually, as we kind of further iterated the problem, we had all kinds of additional cases that we needed to handle. So one of the things we discovered is that when someone kind of uploads a document, they would automatically be like, oh, I scanned it upside down. Let me just delete that one and do it again. Or they noticed that they'd actually kind of combined 2 or 3 different documents all at once, and they would say, okay, let me delete that, let me upload it again as 2 pages. So, I mean, they were wasting a lot of time doing that, but when they just kind of dumped it all onto the fax machine, we had all of these problems, things that were upside down, things that were multiple documents submitted as one fax, or sometimes one fax, one document that was split across multiple faxes. Pages that were out of order. Other kinds of edge cases that we hit were, we wanted to classify things this way, but in this weird case, we need a very customized special rule that this one customer really needs, and you need to classify it in a different way. So there would be like cases like that. And then there would be cases also where we had sort of like a tree of categories that was important. And again, those actually tended to be rule-based, where one practice based on their specialty or based on other particulars of what they did, were they would require additional further categorization. So this is, let me actually talk a little bit about page splits in particular, because that was something that we took a little bit of doing. We started with a whole bunch of documents that had been split manually. So we were starting this after some time. We had data based on both our users and also our own staff had kind of gone through and split a lot of pages, determined where the page splits should be. And actually, it's something that can be extracted generally from the database. But what we could compute was, well, okay, if these 2 documents are part of the same, if these 2 pages are part of the same document, then what's the kind of like typical similarity of those documents? Versus if they're for the same medical practice, but they're not the same document, what is the kind of page-to-page similarity there? And in general here, we're talking about OCRing all of these documents, so we're treating them like a big bundle of text. So you could say, well, okay, for when they're part of the same document, you'd get something like 40% overlap maybe in the words when they're part of the same. But when they're 2 different documents, it would be something like 25%. So that was one input. The other thing that we came up with doing is classifying all of these pages in terms of how likely they were to be starting a document, a singleton page, or starting a longer document, If you think of something like a fax cover sheet as the most trivial example, that's actually almost always the start of a multi-page document. So even if it has no words in common with the subsequent page, you can guess that it's likely part of what follows. There's certain keys that we found that also identified this is the end of a document, or something that actually, certain keys that were an interim page. Then actually combining all of these things actually became very accurate with some tweaking and some modifying of the different parameters.
I have a question.
Yes?
So are these features that you're looking at on these pages, are these like OCR words on the
Typically,
pages?
actually, that was what we started with, and that's what got us a lot of mileage for a very long time, is simply extracting out the words that OCR got imperfectly.
Right. And then like seeing if it said like end of transmission or something.
Exactly.
Okay.
Later on, when we got a little more sophisticated about it, we could do things like, well, if you see something that looks like a logo here, just dump an extra word at the end of the OCR output. And that actually would be another feature that the classifier could consider. But 90% of it are, some very, we got a lot of the gains just from looking at the pure bundle of words that came out. Also, you could actually run a rule set on, well, if you have words in this particular sequence or a whole sentence that looks kind of like this, then that might also be, add a token at the end that says we saw a sentence that looked like that, and then you could kind of just throw that into the same algorithm that we were normally using. So we would kind of take all of these steps. We would say, okay, let's split up that whole long, 50-page fax that we received into 40 smaller or 25 smaller documents, and then classify all of those. So we would kind of go through, put it through the entire machine learning process, and then take that data, perform some further manipulation there, and then feed it to kind of a similar algorithm yet again. So this is what kind of we evolved to over time. Actually, this is what we kind of like had in mind when we started, and then I'll show you where it evolved to. So we thought we'd extract some data, we'd have a beautiful, clean kind of matrix of particular, like almost like a matrix of numbers. This word was seen 8 times, that word was seen 2 times. Then we'd be able to like apply this particular machine learning layer. Actually, we thought we were kind of going in the direction of APL, which we did. It's like a array programming language. And then we would be able to output something very nice and clean, and then we would be able to load that back into the database. And I actually, I'm sure that many people here from the machine learning group have had many problems where it actually does sort of resemble this, at least conceptually. But we didn't have that, actually. We ended up having something very different, where sort of like extract some data, you'd extract a lot of more details than we originally thought we would have to extract. We couldn't just like isolate it down to a very small number of inputs. We'd have to have, for example, which phone number did this fax come in from? That was important. What time of day? Like basically we would start adding more and more metadata kind of as inputs into this overall equation. We would have a machine learning layer, then we would actually run more business logic, then we would kind of partition the data set in various ways, then we would kind of run through the process again and again. We would have a whole long sequence of different things. We couldn't isolate it out to just one pass with machine learning.
What did you have under the machine learning layer? Was it artificial neural network, or what kind of, what did you run?
We did not, I mean, we experimented with neural networks, but for the most part, we actually ran
Bayesian?
well, TF-IDF
Yeah,
and Bayes classifiers.
Bayesian usually has, it's corrupted as more data you have. You can look to another things like best match 25. Did you look on probabilistic algorithm
we
to
have.
BM25?
I mean, so you're right, and I think that there's actually a lot of techniques that could be used for this kind of more of a hierarchical classification scheme, I think is what you're getting at. So that part of the challenge, and again, this may be something about of a practical challenge, is that when we would come up with a particular kind of thing that was wrong with the output of the machine learning, sometimes we could say, well, we can improve the algorithms, improve them, and we can kind of solve the problem that way. And sometimes we would say, you know what, there's really no way for us to solve this on that layer. we really want to apply some business logic. We really want to say, well, that customer really wants a special rule that would say classify all of these things in a particular way, and then put them back through the pipe in another way. So we would end up having this business layer logic and then feeding it back through. And I think that, again, there's maybe a bunch of different things, different ways we could have solved that, but that was kind of the reality of the situation, is that customers would have these different
When
ideas.
you mentioned the metadata, like the phone numbers of where the faxes came from, so did you get some conclusions that some phone numbers were more reliable than others, that they would produce faxes with less errors?
No, well, yes, but that was basically because the OCR would be cleaner from some of them. One of the reasons it was an input is simply because if you're getting it from a CVS, you have a very good idea that this is one of the different pharmacy types of forms that you could get, like a prescription renewal or a refill request or some kind of something like that. So it was just another feature that we could employ in our classification.
Beyond the incoming fax phone number, did you need or did you think about getting like some kind of personalization on who it was that was actually sending the fax, some kind of ID on the actual employee who was doing the faxing?
Oh, well, so those would be just from the, oh, I see what you're saying.
Because some people might be less
Okay.
trained.
Well, so let me explain that. So actually, there was, that was kind of like treated on an ad hoc basis, I guess. Yes, like there would be times where we would notice that we got a 0% classification report for some practice. We would discover they were kind of putting the faxes in upside down or something like that. But I guess just to clarify a little bit how it worked, typically we would get a mix of forms directly from the practice themselves, where the user, like a receptionist, would be dumping 50 or 100 pages on their fax machine and sending it to us. And then the other things would be fax transmissions that we would receive because we rerouted their fax line to us. So from CVS directly, or from another hospital.
But when you have like some concept of like this practice has 5 receptionists, this practice has,
We never, I mean,
do that.
all of that was in the system, but it never affected this layer. Here's what here's the direction that we kind of ultimately went here, which was we decided that as much as we would like to have this clean machine learning layer, and I was very excited about it, I think we all were, we found that when we were in this very lengthy exploratory phase of how much can the machine do, what is it going to do, we're in negotiations with customers about what they want the classifications to do. What we found is that we were alternating between a kind of business logic layer and a machine learning layer. And when we were kind of running things, again, if we had sort of gotten Perl to work well with and effectively in our machine learning phase, I think that would have worked well. But we weren't, so we had to kind of alternate between a Perl layer, a APL layer, or going out to these binaries. And then we would go back into Perl, and so on. And a lot of the time was just spent either dumping to file, reading from file, or kind of marshalling that data in some format, like bringing it in, interpreting it, converting it back into the objects that we needed to run all the complicated business logic that we would have. So that slowed us down, I'll say, in the exploratory phase. And we came up with the following kinds of principles that applied to us at the scale that we were working, which is, okay, avoid the disk as much as possible, basically pull things up once. Avoid streams, by which I mean we tried saying, well, maybe you can kind of have the machine learning process running and you have the Perl process running, and they can communicate back and forth with each other through streaming data, basically through pipes. I actually think we might have been able to push there, but it was a lot more effort than we initially thought, and it didn't ultimately kind of work. And then we also discovered that a huge amount of stuff can be done just in memory, which is something that hopefully a lot of machine learning people have seen one way or another. You can isolate the data out for a particular algorithm, and you can kind of get it all into memory at once, and you can actually do phenomenal things by just very fast. Either as when you're running a program in just as part of development, you can still deal with tens of millions of rows or hundreds of millions of rows easily, and certainly in production with a big box that has a huge amount of gigabytes of RAM and so on, you can actually do a tremendous amount just in memory.
When we do classification and machine learning, we have a true positive, true negative, and so on. So we don't have 100% match. So what was your percentage? How much was the good match of classification? 70%, 50, and what you do when it's the middle? It's not never 100%.
No, absolutely not. And actually, the first production version of this had a success rate of about 25%.
That is less than random.
No, because it's actually out of 40 different categories.
Yeah.
So
okay.
It's actually quite a bit better than random. And what I'll say is that 25% rate that's not the rate at which we got it right. That's the rate at which we guessed. So what we did is we created a cost of, a business cost, penalty function really, of getting a wrong guess versus getting a right guess. And we, based on the kind of confidence that the machine learning algorithm would spit out, we would say, well, we're going to get a lot of these right if we guessed 100% of the time. But we said, okay, with these 25%, we had a near 100% accuracy rate. And so we're only going to guess on those 25%. And unfortunately, again, the business was a little bit risk averse, which I think is in some ways appropriate for a healthcare setting. We set the threshold at what the error rate of humans, trained humans in our company were, not the humans at the practice. So the customers didn't have to be worried about it at all, that it was automatically classified. And actually, we set it at what we estimated our own staff to be their accuracy level, but we actually generally beat them. So again, we were not doing the vast majority, the majority of the documents were still being classified or touched by hand in some way. We were only to be able to kind of take it through all of the different steps about 25% of the time, but those were accurate and they were saving millions of dollars for the company.
In your computation, did you take all the attributes from the documents, or you just select certain?
Good question. So there were certain categories of documents that required some things like matching on a patient's name in a database and things like that, that we never, I would say we were only partially successful at that stage. And the risks of getting that wrong were extremely high. So that was like one of the last steps that I worked on before I went to a different company. And I'm not totally sure.
Yeah, you must exclude certain attributes.
Exactly, yeah. And again, that would only affect certain categories of documents. So those are things we couldn't necessarily do. Here's a few caveats, I would say. Again, this is my personal experience. Some machine learning problems you guys aren't necessarily in the same situation that I was in, where I was working as a web developer, generalist web developer. I was spending half my time doing JavaScript and CSS and things like that, and we were just trying to reduce costs here and reduce CRUD. But we had to explore our way to well, what can we really do? What's actually going to, in practice, save money? For us, when we were doing a lot of kind of porting back and forth continually between kind of like our business logic layer and our kind of machine learning layer, we wanted to put it all in the same stack. We didn't want to be porting between two different technology stacks and two different libraries, even though we had people who kind of were familiar with both of the all the different languages involved. But as the company evolves and becomes more sophisticated, I think a lot of people will still find that mixed stack is useful. And I think that's, I'm not trying to put that down in any way. And I actually think that there can sometimes be value in having two different technologies. I've heard some people be great advocates for saying, well, you should use the tool that's appropriate to that particular problem. You shouldn't try to just all cram it into some very general language or tool set that kind of does everything poorly. So I'll just say that as a caveat. But what I really wanted to get to was why we, after getting that stuff wrong and actually making worse errors in a second company that I thought was not going to do machine learning at all. But so we made it all on Ruby on Rails, and then we ended up doing all this machine learning stuff, and it was horrible to port between Ruby and other languages. Didn't want to necessarily kind of share that nightmare with you, but what I did want to say is that after all of this, we came to Clojure, and this is what I think Clojure is very effective. It's actually perfectly good at all the web DB stuff. Like, it's a very good general purpose language. There's great libraries to make a quick web app. All of the kinds of stuff that you typically see in web apps, you can either find a great Clojure library for it. You can also find Java libraries that are very useful. Domain logic, if you're in some complicated domain where you do have a lot of kind of complicated business logic, like healthcare, or in Unfold's case, a different set of problems, Clojure is great at that. It's a very high-level, concise language, and it has a lot of utility. And then it's very well suited for building some algorithms, and I wanted to go into a little more detail there. One of the things that I didn't necessarily know about before I got into Clojure, but I found very useful, is number one, there's just a kind of philosophy of small composable bits. I don't think this is intrinsically built into the language. I've seen many Clojure users who don't necessarily write Clojure code this way, but Rich Hickey, the creator of Clojure, has been pushing this aggressively, and it turns out to be a great philosophy for the kinds of machine learning problems that we've seen. You can kind of make a simple function that maps from one data set to another. You can find different ways to compose different list processors and reducers, and that actually is very powerful. Again, that's a feature I see very much in APL and languages that were designed specifically for kind of hardcore numerical analysis, numerical processing, but Clojure has it too.
When you say APL, are you actually talking about like the language with the special keyboard,
Yes.
the symbols?
Well, yes. Well, okay. So we never used a version that had all the special keyboard, but there's like these kind of variants on it called like J and K, which we have used, and so they kind of make it. You don't necessarily need the fancy keyboard to do it. Actually, even with APL, I think there's ways to use it without.
I didn't know that was actually in use aside
Oh,
from
absolutely.
like YouTube videos.
Yeah,
of,
no.
like the Game of Life.
Okay. No, it's cool. It's powerful, and actually, it can do a lot. It's not.
I've been very impressed
Yeah.
by it. Don't get me wrong. Yeah.
Yeah, I mean, it's true. You can. I think the things that you see are like Game of Life in one line of code, that sort of
Right,
thing. Yeah, I
right.
mean, it's very, very.
I thought you were
concise
using
language.
APL as like short for array programming language, like R. That's what we use in these guys.
Yeah, no, we
Right.
I think R is a great language. We didn't end up kind of going very deep down that path, except for we would use it for like in sort of like offline activities, like we want to generate a pretty chart for this and so on. But going back to this, a few other things about Clojure. Almost everything is a sequence. A lot of things implement the sequence interface, so it actually makes it very, very easy to kind of port things back and forth from one context to another. Like by default, you're not kind of constructing a complicated language the way we were in Perl. A complicated object and calling kind of a whole bunch of object methods. By default, you're kind of keeping things in sequences, in maps, in lists, in vectors, and these kind of slightly lower level types actually allow for a lot of flexibility in this kind of exploratory programming phase. My example here is in Cantor, which actually there was a Clojure talk earlier where people discussed in Cantor. It's a very cool library that implements a lot of classifiers and other kind of machine learning tools. And it actually uses an internal format that is optimized for kind of numerical operations. It's very useful, but the nice thing about it is you can actually just dump your list that you are kind of keeping your data in anyway into Cantor. It's basically trivial to put data into it, and it's pretty much trivial to get it out. Like you don't even really have to think about it. So there's much less friction when you're kind of navigating between different modes of processing data, kind of a business logic heavy mode and a machine learning mode. Let's see. I thought I would just very briefly mention like an algorithm, and then I kind of decided not to go into too much detail on the code because I thought it would go a little on. So the technique that we've actually ended up using both at athenahealth and also at Unfold is called TF-IDF, which is term frequency, inverse document frequency. This is not necessarily a highly sophisticated machine learning algorithm, but it's actually quite effective. It's a simple kind of classification tool.
Exactly. What this algorithm lacks is that you are not measuring the terms, how close they are to each other. You're just measuring towards the whole.
Exactly.
And that's your failure. That's your first bad classification because actually terms that you're looking are next to each other, very close. If you want to have a term and at the end of the documents, you will classify them same, like if they would and that's why you have to use best BM25. And just as a rumor has it, probably Google used best match 25 also.
So
TF-IDF has a weighting mechanism, though, right?
Yeah, weighting mechanism. But in the weighting mechanism, when you have a document and you have a corpus and you throw the documents against that corpus that you build, and let's say have some medical information, you get the relevance. How much relevance? If you have different corpus that talks about politics and you have a medical corpus and throw against the political, you get low weight. So you know that most likely this is the corpus related. So that's how it is done.
I absolutely, I'll second that.
So you cannot do this algorithm.
I think this is a good
classification.
point. This is a good algorithm. What it does is it basically just counts up the periods.
This is
in a
basically
particular
search
way.
engine. What is this? This is a Lucene search engine.
Yeah. So
This is nothing more. This is not probabilistic search.
So here's why I guess after running through probably 20, 25 different algorithms, this one actually turned out to be effective, for example, for athenahealth, is because we're actually not getting much prose, right? So we're not getting sentences, we're not getting documents that have long written out things, hardly ever. Almost always it's like kind of what I call semi-structured data. It's not like structured in the sense of computer data. It's a form that has like a few scattered keywords on it, and so on. So this actually turned out to beat a lot of other algorithms once we kind of properly tweaked it. I completely agree with your point, though, which is if you're classifying web pages or you're classifying something where people are writing like kind of a human language, I would suggest, use this cautiously. I would say what you often want to do is extract meaning from word proximity, from which words appear next to each other. And so I agree, and I think it's a good point. Here's a couple of things. Even if you're using something like this, the way we were, you still need stop words, which are words that you need to throw out. You still need some thought to how you want to tokenize for your particular domain. So if you're doing a whole bunch of OCR text, for example, there's certain artifacts that are generated through whatever OCR program you use. So you want to kind of have your tokenizer or preprocessor kind of be aware of those and kind of treat those correctly. Smoothing is something that actually also can be helpful depending on how many training documents you have, because you don't want to kind of overfit your algorithm. I don't want to get into too much detail here, but there's like a few of these things that you want to kind of apply above and beyond the basic formula that's listed here, which is again extremely simple, and it's all on Wikipedia, and it's very, very simple. But I would say that in Clojure, like all of these features are essentially added to this one library that we found in under 30 lines of code. So even kind of when you go beyond the simple mathematical formula, and you need to kind of deal with all the practical stuff of having a realistic classifier, the Clojure version is very concise and very simple. And I'd rather do all of this kind of stuff in Clojure than in MATLAB, for example, where I don't have necessarily a good regular expression kind of interface and so on.
So I'll give you an example where this is going to do misclassification. Let's say you have a document that has, I have a black head and a red car, right? And now you misclassify, let's say, I'm looking for somebody with red hair. You're going to have match over there because they are not close together, but they are in the document. So you see, that's where you have lots of misclassification using this TF-IDF.
I think the thing is to point out this TF-IDF. I think the whole point is to show how easy it is to write something like TF-IDF.
Yeah. Yeah, and again, there's many algorithms that are appropriate to your
Well,
particular problem.
There are
I
much
wouldn't-
more advanced techniques,
Yeah,
you know.
Wait, I have another point. So when you talk about like the downfall of TF-IDF being that, you know, you've got these different subjects, like when you use TF-IDF in Lucene or Solar,
Yeah.
it's actually TF-IDF per field, right? And it's not TF-IDF across every single word that you're indexing. So does that make up for the downfalls that you talk about with TF-IDF?
I'm not very familiar with this new Lucene. I tried a couple of times Lucene, and I'm not familiar with this field.
Like
I
I do
would say
Lucene and Solar stuff all day.
Because
right?
usually
And
when
they
you
use
index,
TF-IDF,
it's one
right?
index.
And its TF-IDF relevance is per field, right?
Mhm.
So like if I have two fields that are first name and last name, I'm gonna have one TF-IDF measure for first name and one TF-IDF
Okay.
measure
Yeah.
for last name, and they're not gonna get confused. And if you're using TF-IDF to where you're going across fields, then you're using it wrong.
Well,
So you have to have a structured data. So you're talking
Right.
about where you
Right,
have
yeah, it's just
all
structured
everybody has a same attributes, but there are documents that are unstructured, and you have to classify
right,
them.
right,
So it essentially has to do with how big your fields are, right? So if your fields are like 10 pages of text, I think it's very clear that, and especially if they're like natural language text, I think there's a very strong reason why you would want something that works differently
Right.
as part of your classifier. And again, there's a range of different techniques that can be used.
It is what we do, is our job.
But yeah, but
Find the best
I
ones,
agree
right?
that I feel like I'm sure that lots of people are dealing with these kind of processing large reams of natural language processing, some, and I've done some of that, 90% of the problems I've seen have not been processing large reams of English text.
Right.
Is this
So-
what you ended up implementing, TF-IDF?
We did end up implementing that.
Is it possible to see the?
Oh, sure, yeah, I can click on the code here. So this is actually by Ignacio Pierre, who's actually a very cool guy. This was on Hacker News not too long ago. This is not actually my code, just to be totally clear about it. We actually don't use a standard version of this at Unfold, but we used a fairly standard version of this at Athena, I'll say. So here we, let's see if I can make it a little bigger. Let's do it raw. Okay, so essentially there's stop words. I mentioned that. You tokenize, in this case it's loading it actually from file, which is actually one thing that I would recommend not doing, avoiding as much as possible. Mixing in any kind of disk access with your machine learning algorithm, but that's fine.
Is there any way you can
Oh, sure, let me see.
Oh,
Yeah.
gosh, thank you.
Okay. Is that, okay, this will look a little better. Yeah, there's stop words which are, in this case loaded from a file, like a bunch of words that you just don't want to consider because they're more likely to throw off your classification than they are to contribute valuably to what you're doing. That actually can be very much domain specific, by the way, like depending on what kinds of documents you're working with. For example, we would have all kinds of stop words that were particular artifacts of the OCR process. Like if you had like a corner of a form or something like that, that would often be like, it would turn it into, I don't know, like an L or something like that. And you were like, well, a loose L like that should be a stop word. Tokenizing, again, you're kind of dividing up your document to separate specific tokens. You're using each one as a possible indicator of a class. Then IDF refers to inverse document frequency. It's basically, you're saying, you're comparing the prevalence of this term, its appearance in your overall corpus, essentially. So does this word appear very frequently in general? Like, is it, or is it something that actually doesn't appear that often, except for when it's associated with a particular class? And then term frequency is its association with a particular class. So, I don't know if we should kind of go through this in great detail here, but certainly for the machine learning people, if you guys haven't seen Clojure, it kind of gives you a sense of, hopefully it's concision, and hopefully not that it's off-putting or anything like that.
What I would think probably now, when I look at these actually medical records, I think decision tree would be good classification.
Yeah, absolutely.
Because
Actually-
you could actually look like cancer. If you have a cancer, do I have a chemotherapy? Do I have this and that? Actually, you would do several type of trees, a decision tree.
Yeah.
But I think the leucine is, in my point of view, it's completely useless. I don't think this is good, but you have to go
Yeah.
different direction, I believe.
Yeah, no, I mean, we did a bunch of head-to-heads, and, you know, the problem with doing a head-to-head is you don't know for sure if you've implemented a particular algorithm correctly. So it really does require some theory as well as some kind of practical experimentation. Again, I actually believe the theory is sound on why we did the term frequency and document frequency for this kind of unstructured text. And it was actually quite effective, and it did beat out and kind of shoot out against the other kind of algorithms we tried. And we actually did look at some decision trees, and I've used them separately, but not for this particular problem.
What measure do you use to compare different things that you've tried?
So, well, the penalty function, basically. So, it's, again, we actually turned it into dollars. Like, for every thing that you guess on and you get wrong, it's like a $10 penalty or something like that. And then for everything that you don't guess on, that's like a $2 penalty, for example. These are not the actual numbers. And then for everything you get right, you could say that's a $1 win, and you want to kind of basically just adjust for the ratio of those things, or which one kind of will earn you the most money at the end of the day. And then, so we would kind of iterate them. We would have some amount of time for parameter tweaking, so we could try to get it to optimize for which one did we end up with the most money in at the end of the day. And we would run it obviously on the whole sample corpus without actually using that data, of course.
Did you also try like simulations and like taking your documents and just rearranging them or doing things like that?
You know, we only in a very limited way. So for example, like if we had a whole bunch of documents that people were uploading one by one, we knew that that was actually pretty close to what they would look like if they hadn't split them. So for example, so we would reconstruct a training batch based on kind of essentially concatenating a whole bunch of things that people had done. But you know, we didn't get into a lot. We could have, actually. I think we could have done more.
Yeah, I was just curious, how much did your implementation stick to the concision of what we have on the screen, or did you have to,
Yeah.
maybe write some of it in Java or optimize some of it? How clean did it end up being?
You know, honestly, it's pretty short. Like our code, like again, we're trying to focus on when we have like a machine learning algorithm that implements a core algorithm. We're seeing a lot of libraries that are like about 40 lines like this, in terms of where does that evolve as we grow up, I can't say for sure, but right now it feels really clean and good a lot of the time. And again, that doesn't mean that the overall scope of the project is simple, because we actually spent plenty of time doing the business logic side and then going to this. And I'll actually mention that when we were doing this in our bad way, which is, you know, business logic separate from machine learning layer, we had so much code, but a lot of it was just controlling for, you know, converting the data, dumping it, pulling, all that kind of ETL stuff was kind of, which is extract, transfer, and load, I guess. All that stuff was kind of taking up tons of our time and tons of our code base, and it's kind of like infesting it in various places. So, you know, the actual, like, implementing the math part wasn't necessarily that bad, but we would end up with a lot of kind of cruft around it.
So this was for old company,
So we actually use, so we use TF-IDF extensively at Athena Health. We've used it a very small amount at Unfold for certain things. And the old company was never, I never used Clojure there. It was like not available at the time.
Machine learning algorithms usually benefit from parallelization. Is it easy to multi-thread in Clojure? And are there libraries that perform matrix operations that are parallelized on the
Good questions. Yes and yes. There's a bunch of kind of parallelization kind of primitives that are built into Clojure. They're actually very nice and very easy to use. Essentially, you can just turn your map into a parallel map, and it's good. Now, if I really had to optimize it, I do think that having to drop down into Java would be necessary at points. I haven't yet in practice. In terms of your second question, libraries. Incantor, I mentioned that very briefly, is actually great. It's kind of inspired by a lot of stuff that's in R, and internal representation is a kind of matrix representation that is more efficient for if you're doing certain kinds of like hardcore math. A kind of middle ground that is often very useful if you kind of don't want to go into the whole Incantor, because you do have to kind of adapt a little bit to their kind of API, Incantor's API. A middle ground is, Clojure again is this sort of like high-level language, kind of dynamically typed language, but you can add type hints to any individual function, so it kind of knows that a particular vector is going to be full of numbers, for example. And that actually can get really good performance in a lot of practical situations that I've seen. So
You might want to point out that Clojure has a lot of immutability built in just so that the multi-threading works smoothly.
Yeah, that's true. It's actually was part of the very initial part of the language, and it's very cool.
So once you decided on an algorithm that you want to investigate further, do you go straight to Incantor, or do you take a look at how they implement Incantor and sort of like roll your own, or do you look for other Java libraries like Mahout, or what kinds of things do you do? What's your thinking process?
Yeah. So, I think a lot of it, the initial part of it really is kind of understanding the theory of like, well, what is this technique meant to do? Yes, in terms of like finding an existing library, I would prefer a kind of Clojure native, and I found that some of the time, maybe 50% of the time, there's something someone has posted somewhere, or is part of Incantor, which has, Incantor is not comprehensive, by the way. It's like, it's missing a lot of things. But that said, it's also great because it actually has way more stuff than you might expect. So Incantor, if I can find a Clojure native library, I actually haven't used Mahout yet, but I have called into a number of other kind of Java libraries that exist that have been handy.
Have you used Weka at all?
I haven't.
It's really nice. It's got a lot of these different types of classifiers all built in.
Okay.
So it's really cool.
What was the name?
Weka.
W-E-K-A. Have people wrapped it?
Yeah, there's wrappers, but I don't even know if you need them. I mean, I'm not sure that those wrappers would be good abstractions around Weka functions. I mean,
One trouble with Weka is that it's under the regular GPL license,
right.
So that's why we were unable to use it at our previous company.
Right. If you're going to be releasing software, you can certainly install it on your servers.
Yeah, but I mean, for releasing stuff.
Right. But Weka is really amazing. Weka is like the state-of-the-art classifier library. It's out of the University of New Zealand. And I've used it in production in a previous company, and it's really powerful. It's great because it'll implement, like, you can take the same data set, the same features, and you can see how accurate it is using TF-IDF or Bayesian classification or like an ID3 tree, and literally like 100 different implementations of classifiers, and you can see what your data would come out looking at the same thing. So, like, it's amazing.
And it's easy to specialize. We made our own version of one of their decision trees. Things by
Right, I think you're talking about you had to like rewrite it
Yeah,
for release, right?
Well, we made our own version by subclassing their decision tree stuff, right?
Right.
But then because of the GPL thing, we ended up like reverse engineering it into our own code so that we could have a different license.
Yeah, I've got a lot of.
How you were successful with ID3? ID3 is pretty good. I like the.
Yeah, but there's actually, I mean, ID3 is still like 15 years old, and there's been refinements on it. I'm trying to think of like the one that the best ID3 tree. I think it's like RJ45 or something. But I also think that's a phone jack too. So but there's an ID3 derivation that's like a few years old. That's amazing.
What is your corpus? How many documents you use? J48. How many documents you use to train your machine?
So, like for example, the
To
The
create
fax document classification.
yeah, for classification, how many
Um,
documents? Like, what is the corpus like?
I would say probably on the order of like a couple 100,000.
100,000?
Yeah.
That's not bad. That's small.
Why would it really stuff like boosting too? It'll
Mhm.
take the things that it couldn't quite classify, and it'll go through and reclassify those by some other different algorithm and see if there's something that comes out useful. It's really
Did you ever try just Veka? Did you ever try Veka? Work with Veka?
I haven't. I mean, I'll take a look at that though.
It's fun.
Yeah.
It's from New Zealand. It's pretty good for getting some idea about the data, and you can quickly apply ID3, RJ, all these trees.
Right.
Yeah, a neural network is one of the best,
Right.
one of the best classifiers. Yeah.
Sure. So actually, that's pretty much the end of my talk. I
Are you going to talk about
well,
Unfold?
yeah. Let me talk. Yeah, it's true that the title of the talk I didn't really quite live up to that one. So I'll say briefly about Unfold, and I think that we're still kind of like early, and we're still at the stage where we're actually throwing out as much kind of classification code and code in general as we are building it. It's very much in the early stages of exploring the right feature set and so on. But let me kind of give you guys a little bit of a story of what Unfold does. Our idea here was to make news more useful in an age where a lot of what we get through news or just online is different people's opinions. We're interested especially in politicians or pundits or experts in various fields, economists or legal expert, for example. And all of these people kind of are quoted in news stories, they're in blogs, they have their own Twitter accounts sometimes. And our idea was, as news junkies, we wanted to find a way to say, well, can I get a summary of any particular issue, like Mitt Romney's tax plan, or is global warming going to be 2 degrees or 1 degree next year? This sort of thing. So we kind of evolved into something that we call Rotten Tomatoes for the news. Basically trying to collect all of the opinions we can and focus on notable people, not necessarily every last person on Twitter or on the internet. So basically, in terms of trying to tie it up a little bit into machine learning, the kind of useful tools that we kind of built early on that have kind of remained useful to us actually are just those that identify that possibly a new opinion was expressed. So it actually doesn't tie that closely into a classification problem, but we do use some of these kinds of techniques in a slightly more subtle way, where we try to say, well, how likely is this that this is an opinion that we haven't seen? It's distinct from the 40 times that Mitt Romney has said something about taxes before. We want some kind of like probabilistic score. And then in general, we actually put it in front of our editors. We have like a small team of editors, like a couple are full-time, and then we have some that are like kind of part-time, work remotely, that sort of thing. And they do a lot of kind of hand curation of a lot of things. So certain things the machine learning can do on its own. A lot of it is what we call like the cyborg approach, where it's like machine learning can do a ton of filtering for you, and then ultimately a human needs to touch it as well, and the end product is really a product of both of those kind of working together. So I actually would love to do a field report on that at some future point. Maybe, I don't know, we'll find out. Maybe sometime if people are interested. I'd love to go into a little bit more detail once we have a little bit more, we've seen a little more about how it turned out, basically, a little bit further down the line. But if people have questions about that, I will answer them. It's not at all about being stealth mode or anything like that. I thought this would be a clearer example. Yes?
So I was curious about your approach to this machine learning. Once you kind of train documents in, the system really get any better, right?
Actually, it does in a few different ways. There's, well, okay, so the basic kind of workflow would be, you train on a whole bunch of documents, and then you kind of classify a whole bunch of others. But there were several ways in which a document could later be rejected. For example, let's say we had a very high likelihood that a document was a particular format, and we turned out to be wrong. that kind of override, a manual override or rejection of our classification would kind of go back in. And we actually treated those in a special way, where they would kind of be overweighted in various ways to try to kind of compensate for kind of systemic biases that were in the training set and so on. So that, I would say that that's the kind of like the main way. In addition, I mean, you know, when you're sort of like training on one set of data and then you're kind of applying that training to classify your kind of test set that you actually want to test, if we didn't get a manual rejection on the ones we classified, we would say, well, those are probably good. So actually we can include those in the next round of training potentially. And again, there's actually some caveats about how best to do that. So there are ways in which the system actually got smarter over time just working on its own. So. Any other? Oh, yes?
As someone who started out your career doing half your time in JavaScript, I'm curious what you think of Clojure script, and if you worked with it in Node.js at all. And you also mentioned Clojure being great because of web application frameworks. I wonder if you have specific recommendations on that.
Yeah, so I think Nora is great. Let me take your second question. We use Composure, just kind of a more raw version of Composure, which I think is also very handy and has worked really well for us, no complaints at all. In terms of Clojure script, yes, we do use Clojure script. Some. We actually ended up not using it for the bulk of the JavaScript we write for various reasons. One of which is that actually CoffeeScript has turned out to be pretty useful. There's a couple of cases where you actually want your front end and back end code to do the same thing. Actually, Clojure script is really, really handy for those cases. So it does help actually. It's quite a bit, and we actually have it in our production code base. It's just that I would say it's relatively small compared to our usage of CoffeeScript.
Is there any use case for that you're aware of for Clojure script on Node.js as opposed to just running on the JVM?
I don't know of one. Yeah, I don't know if do you have any experience with that?
No, I'm just
I think it's cool that you can do it, but yeah, but I could imagine if we had been like a Node focused stack and like all our production servers are mostly running Node and not running the JVM. I mean, the JVM does have overhead that I think, at least the way we run it, is more overhead in some ways than Node does. But you know, we started out running on the JVM, and there wasn't any particular reason to run Node on our servers. Yes.
I thought you all like tried to analyze the opinion of the political news.
Yes.
To me, it's like a sentiment analysis. So kind of for this kind of a problem, there's a challenge that it's not like spamming detection. It's not always true or false. This kind of thing, you have different keywords in the article. Like in the beginning, it's true positive. Like in the end, it's like however something. So in there, I think in the community, kind of just aggregation. So what do you think about?
Yeah. Yeah, the way our system works is kind of like Rotten Tomatoes, where we actually really try to cram everyone into they agree with something or they disagree, like they support or reject it. There's also I don't know if you guys know other sites like Metacritic and things like that, where they actually try to turn it into almost an analog score. It's like out of 100. You know, they try to kind of gauge how much did this person like this particular movie or video game or so on. But we try to put things into this real kind of stark binaries. Actually, sentiment analysis hasn't worked for us there. So we rely on humans, and we use the prior database as a way. There are kind of some automated ways we can do, but what we don't do is look at, you know, their use of the word like great. You know, there's just too many layers of sarcasm and all kinds of things that we've seen crop up, and especially in tweets, actually, for some reason, just completely busted our sentiment analysis. This is like unacceptable accuracy level. So we don't use it yet, but we're interested in it, and if we kind of figure out better ways to use it, or if people here have ideas, we'd love to. I mean, that would save CRUD work for us.
Yeah, it's possible. Don't give up. There was a really cool website. It was called Flick, F-F-L-I-C-K, and they really nailed sentiment analysis of tweets, and then Google bought them. But It was like
There
3
is.
dudes, and they did an amazing, amazing job at it.
So when you're making decisions when somebody's for or against something, based on something that is coming in as input, do you find that things change over time? You have a concept of like, this concept of like identity and state, over time. Somebody's for something and then they change and now.
Yeah, absolutely.
So how do you deal with
Yeah,
that?
I mean, well, we track their full history, right? Like, so if you previously believed that we should lower taxes for the wealthy, and then you later say we should raise taxes for the wealthy, we would
So do you
capture
have
that.
like a
in our
fact
data.
checking component to?
We haven't treated it like a fact checking situation. We've treated it like, well, we're just kind of trying to report what people's changes of opinion are. One thing that we haven't done, but we've talked about, is actually like really blaring it out in our interface, like, oh, this person completely changed their mind on something, big flip flop kind of a wording or something like that. So far, we've kept it very subtle, actually. Not done that to sort of like actively humiliate anyone, but that's something more like my co-founder,
The
designer
rate of
friend.
inconsistency.
Yeah, we could do that. I mean, we have the people who've changed their minds on a lot of stuff, and some of them are the people you would expect. And I think my designer, co-founder, is a designer. He could talk really well about all of the different things that we're kind of looking at there. And we probably will end up doing something just because it's fun, so that
All
matters.
the money that's who's paying him this week?
Yeah. Great. Okay, Aaron.